Oh, hi, Lindsay. You're right on time. We're just about getting ready to start here. Okay, well, guys, I think I'll go ahead and get started. We have a few people in Zoom and we have a few people here in person. Maybe both groups together is like close to 7 or 8 people, which is pretty good. I am recording this, so if you need to leave early or if you miss anything or want to watch any of it again, I am going to send out a YouTube link with this whole session later tonight after we're done with the review. So also, let me just give you my plans here. So I'm going to do this review for a couple of hours, and then I'm going to just migrate into my office for the rest of the evening for office hours. And there is a homework assignment due tonight, and if you got questions about that, we can talk about that later. I know some people have already turned it in, but if you're still working on it and you need any guidance on that, you certainly can come by tonight and get some help. My plan is to try to get those graded ASAP. Hopefully before class tomorrow, I'll have that done so that you guys can get some quick feedback on it. I will post the solutions, as always, into Canvas. So the solutions to the homework will be there. I'm also I do have all of these review session problems typed up and the answers are typed up. I just need to get them compiled. Depends on what order I do everything in. So after the review, I might see if I can get those together for you in case you want to just kind of look at that. But if nothing else, in the review resources folder in Canvas, there is a sample exam. Probably haven't had a chance to do that yet, and it makes sense to wait till the review is over anyway. So there's a review session, or a sample exam in Canvas, and then there's also this review packet, which I am holding on to right here. I would definitely take this seriously because it has all of the important terminology that we've covered in these last few weeks. Exactly what's going to be covered on the exam is going to start with section 4.4 and go all the way up pretty much through last week when we started the integration and covered some of the stuff from section 6.1. So I would go through all of these words, make sure you know what it means. What is uniform continuity on a domain? What does it mean to do a continuous extension of a continuous function on an open interval? What does Taylor's theorem say? What is the product rule? Just a whole bunch of things here, right? Of course, the integration chapter has a lot of terminology, upper sums and lower sums, and taking the infimum of the upper sums gives me the upper Riemann integral and blah, 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 all that kind of stuff. So you're going to want to know those terms, things like partitions and so on and so forth. So that's all in there. But the other thing that's in this review packet is a list of the important results. So I tried to get them all typed out for you in one place. And you guys have already seen a couple of my exams by now, and you probably know that you can get a whole lot of credit for just knowing the definitions, knowing the statements of the results. So there's about 20 of them here, I'm going to guess. I didn't actually count them. It looks like at most 20. Everything from the chain rule to the intermediate value theorem to that theorem 6.2, which characterizes Riemann integrability, and a whole bunch more, right? So you're going to want to know all of those statements. Flashcards are great for that. Take them the next 3 nights, shuffle them up, quiz yourself before you go to bed, quiz a friend, whatever your way of doing that is. Just make sure that you are solid on those things. I am going to set this up to have a take-home component again. So if you do blank out on something, or you're like, oh, I forgot to remember what the definition of the derivative is, or something like that, right? You could, in theory, take something like that home and pretty much ace it, because all you have to do is look in the book. But it's much better, as you know, especially those of you who've done well on the exams before, you know that what you really want to be doing is nailing the definitions and theorems in the exam, so that if you do, have a freebie to take home, you want it to be something that's got some meat to it, some substance to it. So the same strategy, I think, especially if you've done well on the first couple of exams, whatever works for you before, probably is the same kind of thing is going to work for you again, because my style doesn't really change much. It's probably going to be the same as before. Excuse me, I did double star the ones on here that I might ask you to prove. So anything that's not double starred, I would not ask you to prove on the exam. I'm pretty much guaranteeing it. You have to know the statement, but you don't need to know the proof of that statement, okay? But some of the ones that are double starred, you know, every differentiable function is continuous. I know that one's pretty easy. The sum rule, product rule, quotient rule, those are pretty much just from the definition of the derivative. What else? Continuous functions on a closed interval are bounded. And not only was that a proposition in the class, there was then a homework problem that basically used that same proof. So you've seen that one a couple of times. So that's one that would be worth making sure you're solid on. You know, the mean value theorem is in the list. We proved that by using Rolle's theorem. If you remember correctly, you have to create this function capital F of X that is in terms of little f of X, and then the theorem just falls right out. Basically, the ones that are double starred are the ones that are very, that are fairly short, right? That I'm not going to be asking you to remember the proofs of anything that is like a whole page. These should be things that are anywhere from a few lines to maybe a paragraph, right? That's kind of what I'm looking at. The other thing is that when you check out my sample test, you'll see that what I did the last time I taught the class is I gave people a choice. So if they had actually not studied every double starred thing, but they happened to hit one of them that I had chosen, then they could pick that one to work on. So I don't want anybody to feel like, oh gosh, you know, if I don't learn every single one of these proofs perfectly great, I'm going to be in big trouble. It's probably not going to be that way, because you're probably going to have a little bit of wiggle room there. But having said that, you know, we still have 3 days to work on this stuff and try to get it down. The more of that we can do, the better. So during the review session, I was not going to just hash all that stuff out, because the definitions, the theorems, those are all in your notes. They're all pretty much black and white. You can always reference the book as well if you would like to. I would rather work through a bunch of example problems, and I have enough to run through 2 sessions, the one tonight, and then we're going to do another one on Wednesday afternoon, which I'll also send out to you guys. And between those, that's almost 4 hours of doing Math 350 problems. That ought to get people, you know, a pretty good idea kind of what to expect. And I've tried to make these problems not too easy, not too hard, somewhere kind of in the middle that I think might be useful. So, okay, hi. Great. So I was just basically extolling the virtues of this review packet handout. It also gives you a list of things to be able to do. So, you know, some of the application oriented stuff, apply the mean value theorem, apply Taylor's theorem, calculate upper and lower Riemann sums, stuff like that. So there could be some of those kind of computational things that you would need to do as well. So anyway, I've got a bunch of ideas there, and there are a couple of practice problems. I only have 4 in here, as it turns out, but I think that's okay. We'll have enough review session problems in the sample test. I think there'll be plenty to look at. So does anybody have any questions so far about anything, just kind of big picture wise for the exam? Yeah, let's see.
It's just going to go into 6.1.
Correct. Now, I'm glad you mentioned that, because we have started 6.3. I skipped 6.2, and I'm going to skip 6.2. But we did start 6.3, and we're going to be talking about that again tomorrow as well. And we proved even something, I think, from 6.4, which is that every monotone function is Riemann integrable. So you're welcome to use those facts. If I'm not going to write questions that can only be solved using those facts, because that's kind of outside the scope of what I said the exam would be. But if you happen to know a result that's kind of helpful from a different section, you be allowed to, as long as it's something we covered. What I don't want is somebody going into like chapter 10 and saying, oh, there's this result, like 3 chapters later that we could have used. That you shouldn't do. But if there was something from the lecture or from a section of the book that we have covered, you can use it. Yeah. Okay. Okay, so any other questions before I jump in with some practice problems? Okay, and I'm gonna kind of go in a random order. It's probably the way that the exam is too. You kind of jump around, do what you can, and then go back. So let's just do this kind of in a somewhat of a random order. So let me start with number 1 here. And I'm gonna number these, and then on Wednesday's session, I'll just pick up wherever I leave off with the numbering. Okay, so here's the problem I want to start off with, guys. Let's let A less than B be real numbers in R. Okay, and then I'm going to let little f be a differentiable function on R. Okay, and then what I like to do is prove. So here's what we're going to prove. This is a proof that there exists a C in the open interval from A to B such that here's the equation, f prime of C. Okay, so it's differentiable, so I can do this. F prime of C is equal to, and this is a little messy, but it's going to be f of B times e to the sine of B minus f of A times e to the sine of A, all over the quantity B minus A times e to the sine of C minus f of C cosine of C. Okay, it's a little scary. So that's what we want to do. Don't have great, whoops. Don't have great markers here tonight. If they get too bad, I'm gonna have to run up to the office and grab some better ones. Okay. That's no good.
Third one?
Well, that's 3rd time's the charm, right? Not at all. I don't think that, is this one gonna be better? Then it's a little better. Not great. Anyway, we'll make do for a little while. At some point, I might have to go get some better markers from the office because I just don't have enough right now. Okay, so anyway, when you see this kind of question, what do you think? Oh, you got another one? Sure. Okay. When you see this kind of a question, what do you think of?
Take home.
Take home. Okay. that might be a good thought. What do you think of? So the formula, which formula? The mean value theorem. Exactly what I was hoping you would say. Now let's just remember the mean value theorem. The mean value theorem says something about, all right, I got a closed interval from A to B, and my function is differentiable on that closed interval. Of course, here the function is actually differentiable everywhere. So that would include any closed interval. And then what does the mean value theorem say? It says there exists a C in the open interval AB such that f prime of C is equal to f of B minus f of A all over B minus A. This is the traditional mean value theorem, right? Again, I've left out some of the words. If I asked you to state the theorem, this would get you maybe half credit, right? There needs to be some statement about, okay, there's a closed interval. F is a function from that closed interval to R, which is differentiable on that closed interval. And then you could go into the statement here. So guys, when I do ask you to state the theorem or to prove a theorem, I am going to be pickier on the correctness of that than I would on sort of an abstract problem. Because that's the stuff that's supposed to be just lifted right off of those flashcards. Right. Okay, so it kind of reminds me of the mean value theorem. Because I do see f of B minus f of A, and I see B minus A, and I have f prime of C here. But there's this whole e to the sine of whatever here that's making it look really weird. So does anybody have a suggestion how we could reconcile these things.
I have a suggestion.
Sorry?
I mean, I have a suggestion.
Oh, I would love to hear it, Danny.
I don't know. It's because of F prime and C being really like complex and confusing. I would assume usually in problems like this, you would have to find like a substitute function, like a g of x or a g of c.
How about creating another function g of x that would be fitting better with sort of the notation that we have here? I like that idea. I think that's exactly the trick, is to apply the mean value theorem, but not to f. If you apply the mean value theorem to f, you'll get that equation that I just wrote down, which is not what this is. So what we could do is we could apply, now I'm going to give you the start of the solution here, apply the mean value theorem to, and what function do you have in mind that you called it g of x, Danny? Do you or does anybody have an idea based on what the expression looks like, what function we might want to use here?
I'm not 100% sure, but my guess would be to include f of x.
You have the f in the expression, so I would expect the f of x would be in here somewhere as well. Okay. And what else? To the sine of. Okay, so Lila's got an idea to take e to the sine of x, right? Because then your numerator of what you're proving is really g of b minus g of a, right? So that seems pretty reasonable, and we're still going to apply it on the same interval from a to b. So whatever the a and the b are. Okay, let's give it a shot. Okay, so thus there exists a c in the open interval a to b such that g prime of c is equal to g of b minus g of a all over b minus a. So we're thinking about applying the mean value theorem to g. And because we've done that, my numerator here, my numerator just becomes f of b times e to the sine of b minus f of a times e to the sine of a, and this is all over b minus a. So that's a great way of getting part of the expression we were proving to kind of show up in our work. Is everybody with me? So g of b is just f of b e to the sine b, and g of a is just f of a e to the sine of a. I should probably point out, I didn't say it in my solution, I probably should point out that I can still apply the mean value theorem to g. If I had taken this beautiful f of x, which is already assumed to be differentiable, and if I had tweaked it in a way where the new function somehow maybe wasn't defined at certain values of x, or certainly didn't have a derivative at certain values of x, then we suddenly would be more limited in our ability to apply the mean value theorem. But e to the sine of x is a composition of two functions that are both differentiable on all of r. So putting that together with f being differentiable on all of r, you end up getting g being differentiable on all of r. If we didn't write all of that down and we just said we're going to apply the mean value theorem to g of x, I'd probably be okay with that, because that's kind of in the background of the actual work here. But it is good to recognize that. Okay, now we're not done yet. We're not done yet. I've got sort of part of the right-hand side now, but I don't know about this f of c cosine of c thing. So where is all that going to come from?
Get f of x by itself and then take the derivative. Oh, interesting.
Well, I don't think you're totally off track here. If you look at the left side, what do we have? G prime of c. Do we have g prime of x anywhere on the board yet? No, we didn't calculate it. This is the formula for g of x. This is what I like about this problem, is that it not only uses the mean value theorem, it uses the rules of derivatives here. So I actually have to take the derivative of this and plug in C. Okay, so let's do that. So let's note here that by the product, and I think it's the product rule primarily and the chain rule. By the product plus chain rules, G prime of X is equal to, so it's the derivative of the first term, which would be F prime of X times the second, which is e to the sine of X, and then plus the first term is F of X, and then the derivative of e to the sine of X, this is where we use the chain rule, the derivative of e to the blob is just e to the blob, so we put e to the sine of X down, and then we multiply that by the derivative of the blob. So this is using the chain rule, the derivative of sine of X is cosine of X. So now I actually see the cosine of X showing up for the first time. Okay, so let's evaluate that at C then and compare it with the right-hand side. Okay, so let's plug it in. So thus, we have on the left side, G prime of C, so that would be F prime of C times e to the sine of C plus F of C times e to the sine of C times the cosine of C equals, and then we still have the same thing on the right side, F of B times e to the sine of B minus F of A times e to the sine of A all over B minus A. Okay. And now we take a look at what we're trying to prove. And what we're trying to prove is a formula for F prime of C. I'm trying to prove a formula for F prime of C. So over here, I can solve for F prime of C. I can actually divide through, it's just algebra. I can divide through by e to the sine of C on all parts of the equation. Okay, so canceling, or not canceling, sorry, dividing by e to the sine of C, what we'll get is, and maybe I'll subtract as well, and subtracting. Just gonna do a couple of algebra steps in one here, guys, just to save a little time. We can isolate F prime of C. So F prime of C is gonna be, first of all, the right-hand side is F of B e to the sine of B minus F of A e to the sine of A all over. Now I'm dividing through by e to the sine of C, so that has to be put there, along with the B minus A on the bottom. And the part that we're subtracting is e to the sine of C times the cosine of C. And no, that is not right. That should have been F of C times the cosine of C. F of C times the cosine of C. Yeah, there we go. So if we divide through by e to the sine of C, that's what we would have. So everybody with me on the algebra there? Okay, and that is exactly what we were asked to prove. So that's the solution. Okay, this would be a really nice little question on the test. It's ultimately an application of the mean value theorem, but not to F. It's a mean value theorem applied to this G, which you have to create on the basis of what the expression looks like. Okay, because I mean, maybe this wouldn't have worked. We don't know, but it's the first thing I would have tried. It's the first way I would have tried to write that down. Okay, not too bad, right? Everybody okay with that?
Dr. Annan,
Yes, question.
could you move the video just a little so that we can see the right side?
I need
There
to
we
just, I don't want to have to move my camera, so I'm going to slide this back a little bit. Can you see the entire board now?
Yes.
Okay, great. I will just
Thank you.
leave it like that and let me know if you can't read anything. I think I am going to go upstairs and get some better markers here at some point. None of these are writing. I like nice, dark, thick markers. Any other questions on this? Nice. Okay, let's do another problem. Hoping to get through 6 or 7 today anyway, maybe even a little bit more, depending on how much side discussion we have. Let's do this one. So number 2. Let's prove that the function, I'm gonna give you a specific function f of x here, which is going to be the polynomial x to the 4th plus 7x cubed minus 9 has exactly 2 distinct real roots. Exactly 2 distinct real roots. So we have f of x here. And it's a 4th degree polynomial, x to the 4th plus 7x cubed minus 9. Does anybody have any thoughts about what this maybe has anything to do with, or like how we would want to maybe work on it a little bit? Even if you don't know the whole solution yet, that's fine, but just like rough idea, like what kind of bells are going off? What are you thinking about here?
Plug in a number and get a positive and a negative, there's a 0.
So we've got location of roots. So if f is positive in one place and it's negative in another place, then there's a root in between. That assumes that f is continuous. So I think the first thing I'm actually going to write into my solution is the remark that this is a polynomial. So since f is a polynomial, then we do know, and that you can just cite this fact without referencing any particular number from the book. You can just say then f is continuous on R. Because if we're going to use something like the location of roots or the intermediate value theorem, remember you always have a closed interval and the function has to be continuous throughout that closed interval. Right, okay. So we're going to be able to use any of those results. So Lila's idea is to maybe plug in some numbers here. What kind of a number do you want me to plug in first?
0.
I always like to do 0. Okay, so f of 0, if we put in 0 for x, we get -9, and that's less than 0. Okay, and so if we wanted to use this location of roots idea, I would need to think of another value of x that I could plug in and have a positive value. So if it's negative for one input and it's positive for another input, then we can catch a root in between there. Any ideas?
It's 2.
How about 2? Yeah, and 1 actually doesn't work. So I would probably go to 2. So let's look at f of 2. Now, by the way, this is going to be a no calculator exam. So if some of the calculations start to get too hard, you can just say, it's greater than 0. Right? In this case, f of 2 is just 16 plus 56 minus 9. So just to be precise, I guess in this case I can do that. I think it's 63, which is greater than 0. Okay? So applying location of roots, or if you called it the IVT, because the intermediate value theorem, this is just a special case of the intermediate value theorem, but you could say applying location of roots to f on the interval 0 to 2 gives let's say C1, I'll call it C1, which would be an element of the open interval from 0 to 2 with f of C1 equal to 0. So I do get one root that way. Okay. So I've got f of 0 is negative and f of 2 is positive. Now, how am I going to get another root? Because we do need to come up with, this says 2 distinct real roots here. I actually think if you plug in any values of x that are even larger, you're just going to make this even more and more positive. So I don't think you're going to get any more roots to the right of 2. So f of 0 is negative. Is it possible to go
-10.
-10? I like doing calculations with round numbers like that myself. So if we put in something like -10, this will be 10,000 minus 7,000 right here, and that's 3,000 change, so that's positive, right? So absolutely, I like that as well. So let's just say also f of -10 is equal to, and again, if you didn't want to work out the number, and you could just say it's greater than 0. Just because I want to do it. 3,000 minus 9, I think it's 2,091. So that's obviously greater than 0. And so, by location of roots, on the interval -10 to 0, there exists a C2 in the open interval from -10 to 0, with f of C2 equal to 0. So I've got two roots to the function. They are definitely distinct because C1 and C2 live in mutually disjoint intervals. So they're definitely two distinct roots. Okay, so are we done?
No.
I think so far you'll get about half credit.
Should that be f of 0 though?
Excuse me?
The last part of your sentence, should that be f of 0 equals 0?
No, f of C2 equals 0. C2,
Oh, okay.
C2
I
is an
didn't see
element of
this.
the open interval from -10 to 0.
I see what I did.
problem. Gotcha. Okay, so I've got two distinct real roots, but the problem is asking us for more than that. It's saying prove that there are exactly two distinct real roots, meaning that we have to now prove that there aren't any others. We have to prove that there's not 3 of them or 4 of them or 5 of them or whatever. Let's think about some of those other numbers. Would it be possible to have more than 4 roots? It's a quartic equation, right? A 4th degree polynomial. If you found more than 4 roots, then you'd be factoring x minus the first root times x minus the second root times x minus the third root, and so on. And you'd end up with something that when FOILed out would be x to the 5th, right? It's not going to be a 4th degree polynomial. So I'm just going to note that since the degree is 4, f can have at most 4 real roots. So we're narrowing it down. We have at least 2 real roots, but there can't be more than 4. So now I want to ask you, could there be 3 roots and could there be 4 roots, real roots, right? So note that f cannot have exactly 3 real roots. Sorry, distinct real roots. 3 distinct real roots. And can somebody tell me why not? Yeah, what would the 4th one be? If I have exactly 3 distinct real roots, then the 4th one would have to be a complex number, right? Like a plus bi. If it's not real, so if you have 3 distinct real roots, then the 4th root is not real, and so that means it's like a plus bi. But one of the things we know is that about polynomials of this nature is that the complex roots, if any, always occur in conjugate pairs. So you can't have, 3 plus 5i as a root unless you also have 3 minus 5i as a root. Now, this is a fact a little bit beyond anything I've specifically stated before. So it would take a little bit, for me to maybe ask that question. I'd have to think about whether it would work for a test, but I could give a hint, maybe something like that. But the point is, f cannot have exactly 3 distinct real roots. Otherwise, f has a single non-real root, let's just say a plus bi, where b is not 0, so it's an actual non-real root. But such roots must occur in pairs of the form a plus or minus bi. So that's one thing that we would know for sure. Yeah, that's a little bit outside the scope. But basically, the point is if you plug in f of z and it gives you 0, then if you were to plug in f of z bar, then you, which is the complex conjugate, you have to know that bar respects addition, subtraction, multiplication, powers, and all that stuff, which it does. So if f of z is equal to 0, then f of z bar would also be 0, and that would be 2 imaginary roots. So you can't have one without the other, is what we're trying to say here. So we cannot have exactly 3 distinct roots. So what's the other possibility here that we don't want to have? What about 4 distinct real roots? So can f have 4 distinct real roots? Maybe there's no imaginary roots at all. Maybe this function wiggles across the x-axis a few more times that we just didn't detect in our original analysis. Any ideas how I'm going to dispel this idea?
Then we take the derivative, factor it, set it to 0.
Interesting idea. If there were 4 distinct real roots, right? I think I got John's idea here. Let's suppose we had 4 distinct real roots here. So the function is passing through there and there, and there and there, and there and there. Then your function, whatever it is, would have to have, so he's talking about the derivative and setting it equal to 0. You would have to have a derivative of 0 at least 3 different times. Let's just, let's take his idea and run with it, but I'm gonna set this up as a contradiction. Right, so by way of contradiction, suppose, let's say R1 is less than R2, is less than R3, is less than R4, are 4 real roots of f, and they're obviously distinct. So just kind of line them up in order like that. And so then what we can do is we can take the derivative. This is a differentiable function. So we can actually take the derivative. But I guess what I'm going to say first is that by Rolle's theorem or the mean value theorem, either one, by the mean value theorem on the intervals R1, R2, and then the interval R2, R3, and then the interval R3, R4, right? There would exist a C1 in the open interval R1, R2. There would exist a C2 in the interval from R2 to R3, and there would exist a C3 in the interval from R3 to R4 with f prime of C1 equal to f prime of C2 equal to f prime of C3 equal to 0. So you would have to have a root of the derivative in each of those intervals. Now, if I'm going too fast and you don't have time to think about it because you're just writing it down, slow me down because I do want you to be sure you're following this. Right, so on my little picture here, C1 would be maybe right there, and there's C2, and there's C3. They're clearly distinct. C1, C2, and C3, they live in different intervals. And those are places where the derivative is 0, where the derivative is 0. Okay. But let's actually take the derivative, which is what John suggested. We haven't done that yet. Let's just take this derivative here. Okay. Everybody so far caught up? Okay, good. So I'm going to go ahead and take the derivative. However, f prime of x is equal to, so if I just start taking the derivative, 4x cubed plus 21x squared. You can just, so you might be wondering, well, do I have to prove that formula? I would probably ask you to do that if I wanted you to do it, because honestly, that's a whole nother problem now. Like to actually find the derivative of this using the limit definition or something, that would be a reasonable question, but it would be like a whole nother problem in the middle of this thing. So I would be more likely to just say, you can use whatever derivative rules that you know from your basic calculus class. And so we could just write this down. And then we can factor it. So if I factor out an x squared, it'll leave me with a 4x plus 21. And you can just clearly see what those roots are. So which has roots 0 and negative 21/4 only. Those are the only roots. There's only 2 of them. So you're not gonna be able to find 3 different values, C1, C2, and C3 here, okay? So this contradicts the existence of what, C1, C2, and C3 described above. Yeah, so that's gonna end up being a contradiction. So this is actually, it looks like a really innocent problem to begin with, but it ends up being a bit more substantial than you think. If I just said prove that f has at least 2 distinct real roots, then the first part of what we wrote down would have been more than adequate. We just use the mean value theorem twice. Sorry, the location of roots twice, and we'd be good to go. It's this word exactly that makes it a little tricky. It's like, oh, well, we have to actually prove there's no other roots besides the one that we found. Yeah, so that's it. Okay. Questions there? Everybody good out there in Zoom land?
Yep, good.
Okay, I'm gonna go to another problem. Go ahead and erase this here and write up another one for you. I like these problems. I came up with some good ones for this review. Okay, so this is number 3. So I'm just going to remind you here of something before I state the question. I'll actually put it as part of the question. This is one of the double starred results in the review packet, corollary 5.4. So this is one you're going to want to know, but I'm going to remind you right now what it says. It states that if f has a bounded derivative on an interval or a ray, and I think I called it I, which is some subset of the real numbers. So if f has a bounded derivative, then f is uniformly continuous on I. So I'm hoping that that result is in your flashcards somewhere. The intuition behind this again was that if your function has a bounded derivative, then that means it's not unlimited steep. It has a maximum steepness. And because it has a maximum steepness, you'll be able anywhere in the domain to find a single delta that works for a given epsilon. You don't have to keep tweaking your delta based on where you're focusing within the interval, because there is a maximum slope or steepness of the graph somewhere. So that's the intuition behind it. And this is definitely a handy result. I want you to know it. I might give you a function on the test that is differentiable and ask you, is it uniformly continuous? And I will be expecting that maybe you're just going to take the derivative. just convince me that it's bounded. If you do that, you can just cite this result and say, yep, it'll be uniformly continuous. So, but what this problem is asking you guys to do is to show that the converse is false. So in other words, just because a function is uniformly continuous on some domain does not mean that its derivative would have been bounded there. So let's write that down, and I'm even going to give you the counterexample, and you're just going to have to verify it. Okay, so here's what it says. Show that the converse is false. This is not an if and only if statement. By proving, so I'm going to actually give you the counterexample here, guys, that's going to work for this. The function that works nicely for a counterexample is radical x. By proving that the square root of x is uniformly continuous. Now remember, whenever we talk about being uniformly continuous, there has to be a domain given. So I have to give you a domain here, or an interval in this case. I'm going to use the open interval from 0 to infinity. So I'm going to claim that this function is uniformly continuous on that open interval, but does not have a bounded derivative. Derivative, I can spell, on that same interval. So we're going to actually confirm both of those things here. Okay, so let's get to work on this. So there's two things to do here, right? I have to prove that this function is uniformly continuous on I, and then I have to prove that it does not have a bounded derivative on I. And of course, either one of those things are probably, you could think of them as both half of the question. Which part do you feel more comfortable trying to look at first?
The bounded derivative part.
The bounded derivative part, I think I would agree with that personally, because I can take the derivative of this and just see what it looks like. This is just x to the 1/2 power. I think we even did this derivative as an example, or it was in the group work or something. I can't remember exactly where we saw it. But anyway, I could ask you to prove, like if I wanted to, I could make part A of the question, use write down the definition of the derivative. Then the next thing would be calculate the derivative of that. And then the next thing could be prove that it does not have a bounded derivative. So we could scaffold this into a bunch of parts, but I think I'm just going to go directly to the derivative here. So by the power rule, which I realize I didn't really prove the power rule for every power possible, but we'll just do it for here. I'll be very clear on my exam, like what kind of rules I have. So the power rule just says if you have x to the 1/2 here, then the derivative of that is going to be 1/2 of x to the negative 1/2. So I can write that. I don't like to use negative exponents very well. It's not my favorite thing, so I'll just write it using a radical in the denominator. So there's my derivative, and here's my interval, 0 to infinity. So the x's that I'm allowed to plug in is anything that's positive, okay? So obviously, if I plug in a really big x, then the derivative will be pretty small. It will be fairly bounded. But what kind of an x are you thinking about that I might be imagining plugging in right here?
The limit is that x approaches 0 from the right.
Exactly. I would pick an x that's very close to 0, a very small x that's just barely on the positive side of the ledger. Exactly. So so I'll just say which is unbounded on 0 to infinity, since we may take x greater than 0 to be arbitrarily small. So we can take the x to be arbitrarily small, so as x approaches 0, then f prime of x is going to approach plus infinity. Okay, and that's the fact that it's unbounded. If you have a question on the exam, like how rigorous do I want this to be expressed, you can certainly ask me. Like, you might wonder, do I need to prove using the definition of convergence to infinity that that's really what I mean here? Chances are probably not, because that would have been something that would have been limits involving infinity was the second midterm. And this is not going to be so much the focus of what I would ask you here. But if you are in doubt, I am going to be there, obviously. So you'll be able to ask me something like that. Okay, is everybody good with that much of it? So this thing has an unbounded derivative. Let's try to prove that it is uniformly continuous. We haven't done one of those yet tonight. And this is certainly something that's likely to come up on the exam, because uniform continuity is a big part of what we've covered. So f is uniformly continuous on I. I'm going to try to prove that. So this is where we have the definition of uniform continuity. We do have a few results. We know, for example, that if our function is just continuous, and this function is continuous because it has a bounded derivative, means it does have a derivative. It is differentiable, and differentiable implies continuous. So this is f is continuous on I, but that's not as strong as this. Now, if I had been a closed interval, we have a theorem. It's one of our big results, guys. On a closed interval, uniformly continuous and continuous are equivalent. Neither one of them is stronger than the other. I think that was theorem 4.4. It's one of the bullet point items. But this is not a closed interval. So I can't use that result about closed intervals here. So on this case, I mean, we have something about Cauchy sequences and all that, but that's usually to disprove uniform continuity, not to prove that it is uniformly continuous. So I think we're best off here just using the definition. There is an epsilon delta definition here, and I think that's going to be the way to go. So you start off, let epsilon greater than 0 be given. And then that's all I get written down usually, and then I have to go over to the scratch work right away. So come over here, we're gonna do on the side, I'll start writing out a little scratch. The scratch is going to look something like, absolute f of x minus f of y less than epsilon, right? That's ultimately what that would be. And the first step of my scratch is usually just to plug in what the f is. So in this case, radical x minus radical y in absolute value bars is less than epsilon. Okay, and what you would like to get over here is something that is just x minus y, because then you can use the delta. Remember, your goal is going to be to choose a delta over here that we can then verify that delta works. So that's kind of what we would like to get. So it turns out on this one, it's a little tricky, but we can do a backwards arrow here. And what we can say is that the absolute value of the square root of x minus y being less than epsilon is. So if this is true, then I claim that this is true. I'm going to put a little asterisk on this because I'm going to verify that for you in a minute. I don't think that's totally obvious. But if that's the key step, because if that's true, then all I have left to do here, by the way, the x and the y they are arbitrary elements in I. With uniform continuity, if you want, you can always just assume that x is greater than or equal to y. Like if you have two numbers that are kind of equivalent in the definition, in this case, the x and y, you might as well just fix one of them to be assumed to be greater than or equal to the other one. This is without loss of generality. And the point behind that is that you're not taking the square root of a negative number now. Okay, and in fact, when you take the square root of anything, you always have a positive number. So I can actually get rid of this absolute value bar and just write it as radical x minus y less than epsilon. And now I can go one more step and square both sides, and I'll just get x minus y less than epsilon squared. And so this turns out to be the delta that you want to choose. So what you're going to do, I'm going to go ahead and I still have an asterisk to come back to, but let me set that aside for a moment. I'm going to just make this delta choice and see how this works out. I'm going to let delta equal epsilon squared. So this over here on the left is my main proof. So from the scratch, I've kind of figured out what I want my delta to be. And then all it comes down to is you just have to assume that absolute x minus y is less than delta. Which means essentially thus, again, since x is greater than or equal to y, I don't need the absolute value bars. And I can replace the delta with epsilon squared. And now we can retrace the scratch. And from here, retrace the scratch work. There we go. So I can retrace my scratch work now. Is everybody, other than the little asterisk there, which is actually just an algebra comment I need to fill in for you, is everybody okay with the rest of this proof and how the rest of this goes? So uniform continuity, probably there'll be a part A ahead of this that says write down the definition. By the way, if I asked you to write down the definition and then I ask you to prove that the function is uniformly continuous, there's a good chance that the reason I asked you to write down the definition is you're probably going to use the definition to do the next part. It'd be weird for me to like ask you to do part A, which is something that then isn't used in part B. It's like almost like misleading you. Well, that's not the way I write my tests. So you should expect these parts kind of flow in order in that manner. So just a quick little thing about this comment here. To justify this star, I really just need to convince you, I think. So I just need to claim that this guy is less than this guy. Because that way, if this is less than epsilon, then this would be less than epsilon. So I just need this guy, I'm going to state it here. I just need this guy to be less than, I'll say less than or equal to this guy. Yeah, that's what I think we want to say. That's my claim. So if I take the square root of two numbers and then subtract those, I always get something that's less than or equal to if I subtract the numbers first and then take the square root. Let's just see if we can, this is just algebra. I'm gonna square both sides. So when I square both sides on the right, I'll just get x minus y. And when I square everything on the left, square root of x squared is x. I have a cross term of 2 radical xy, and then plus y. So that's just doing a perfect square on this one. I get x squared plus y squared, and then the cross term is minus square root of xy. Now, both of these have x's in them that can be canceled. I'm going to do if and only if again. They both have x's that can be canceled, and I can take this negative y and put it with the plus y on the left. And I can take this 2 radical xy and put it on the right. So I moved things around there, hopefully not too many things at once. we good with that? Well, my friends, remember that x is greater than or equal to y. So if I make this right side smaller by replacing it with 2 radical y, right? So if this is true, which it is, because this is just 2y and 2y. If this is true, then so is this, because all you're doing is you're replacing one of your y's with x, and x is larger. So if this one is true, then this one is true. And so this right here is clear. Radical y, that's just y. Okay. So it's a little bit tricky. I'm not sure. Some of these problems I wouldn't put on the test. But I'm choosing them because they do refresh our memory about important ideas and, important results and stuff like that. And while the whole problem as a whole might be a little more than I would ask you to do all on your own, each individual little piece of it is really pretty decent. Okay, great. Oh my gosh, it's only 8. I am doing so good. Is everybody good so far?
Can you go over the derivative part again? The bounded derivative?
Yeah, so are you comfortable that f prime of x would be 1/2 radical x?
Yeah, I'm comfortable with that, yeah.
Because that's just the derivative of the square root of x as we would have learned it in calculus. And if you just think about this function, Danny, 1 over the square root of x blows up if the denominator is small. So if I have an x value that's really small, imagine plugging in like 0.00001 for x, right? Something that's really close to the edge of my interval I.
Yeah.
If I put in like 0.00001, then I'm going to be dividing by a very small number here, which, when you think about the fraction, blows that fraction up towards.
Yeah.
You see what I mean?
Yeah, I see what you mean.
Okay, good question. Anybody else have a question on this? Okay, so the converse of corollary 5.4 is false. We now have a counterexample. It's kind of nice to know that anyway. Kind of a good one to be comfortable with. Okay, let's do another problem. I think I'm up to number 4, is that right?
Yep.
This is a very typical problem. I give you a function and I'm gonna ask you, is it continuous? Is it uniformly continuous? Is it differentiable? Is it Riemann integrable? All that stuff. It's like a big multi-part question. So here's what we're gonna do, guys. We're going to let f of x equal the absolute value of the sine of x. And I'm just gonna say circle all that apply. And what are the things that might apply here? So f is, let me write them as bullet points here. F is continuous on 0, 1. And then the second one is f is uniformly continuous on 0, 1. And then the next one is going to be f is differentiable on 0, 1. And lastly, f is Riemann integrable on 0, 1. So we'll do all 4 of those parts. Okay. So. If I give you something like this, I think there is something like this in the sample test. The intention of something like this is not that this is a 4-part problem and that you're going to do each of them separately. Because we know relationships between these concepts, and so I'm going to expect you to know those. I'm going to expect you to know that, oh, the first 2 bullet points on a closed interval, the first 2 bullet points are just equivalent to each other. So I don't need to do both of these. I can just figure out one of them and then just use the, whatever was theorem 4.4 to explain that, oh, for a closed interval, uniformly continuous and continuous are actually the same thing. So you should either be circling both of them or neither of them, right? So that's, and actually, if you don't really know the answer, you're like, let's say you just are freezing up on whether this is continuous or not. If you just write down for me that, oh, there's a theorem that says that uniformly continuous functions are always continuous, and if it's a closed interval, vice versa. And if you just write that down, then it's a relevant fact that is part of what I'm getting at for this question. I can give you partial credit for that. Okay, so something like this is gonna be worth a lot of points, because there's really 4 questions here, but if you know how they're related to each other and you can spit that down, then I can give you credit for it. Same thing, differentiable implies continuous. So if this function is differentiable on 0, 1, then there's no need to bother to prove that it's continuous, because we would know that it is. So actually, if it's differentiable, then it's continuous, and then because it's a closed interval, it would be uniformly continuous. So my suggestion on this would be to start with figuring out whether it's differentiable or not. Because if the answer is yes, and you can prove it, then you don't have to prove the other 2. You can just cite those theorems and you're good to go. You don't, the last thing you wanna have to do here, guys, is like 3 or 4 delta epsilons or something like that. You spend half the exam doing that. It's too much, right? There's gonna be some relationship here. So let's actually work on, I'll come back to the Riemann integrable later, because that's kind of a different topic. But let's talk about differentiable first. Does anybody have a suggestion, like what maybe would you try and do first, even before you launch into answering this question? Draw a picture is exactly right. Guys, the thing is, this is the way you're going to proceed if the answer is yes on one of these items is very different than how you'll proceed if the answer is no. These are yes/no questions. And so you want to kind of at least have the intuition of what the correct answer is, so you at least know how you're going to try to go forward with it. And to help you get the correct intuition, nothing better than having a picture. So I would do exactly that. I would draw a picture. So here's my x-axis, and I'm going to graph absolute sine of x. And if you think about how the sine of x looks, it looks like, these arcs. But remember that as soon as you get to, I guess pi is outside of our interval, but it's going to basically look like these kind of arcs. If I wanted to draw the whole picture. Now, we're not looking at the entire picture here, but that would at least give me some idea. You know what, I think I might not be quite happy with that domain. Just a second. Find my question here. I wrote it down somewhere. Oh, yeah, I'm gonna change this question just slightly. It's not gonna make a big difference. I'm gonna change it to, instead of for Riemann integrable, I'm gonna stick with 0 to 1, but on the others, I'm gonna change this to R. I'm so sorry, I'm changing my question. Midstream. Changing my question just a little bit. So let's do that. So let me go grab my drink so my throat can survive, and think about which of those 4 things is true. Well, I kind of told you to start with differentiable. Now, if I change this to R, it does affect this a little bit. I don't have a closed interval anymore. But it will, I think we'll still get away with no more work than we were gonna get away with before. Do you think it's differentiable on R? Just intuition based on the picture. I know that it looks continuous on R. I can draw the whole thing without picking up my pencil. But remember, differentiable is a little bit harder condition. To be differentiable, there should be no
Sure.
sharp corners. Looks like sharp corners to me, right? This does look like sharp corners to me at these places where it's hitting the x-axis. And in fact, we do know, for example, that absolute x is not differentiable at 0, and we did that as an example. And if that's not gonna work, then something like this that is basically built out of that absolute value function is probably not going to work either. My intuition is that this one is a no. My intuition is that this one is a no. It's too bad, because if it was differentiable, I bet it would have a bounded derivative. And then bounded derivative implies uniformly continuous, which would imply continuous, and we'd be rolling. But I think this is probably a no. So if it's not differentiable on R, that would mean that it fails to be differentiable somewhere. And we would want to find such a point and try to prove that it's not differentiable there. What is a point that looks like a promising X value to use?
Pi 0.
Probably 0, exactly. I don't think this is going to be, so I'm gonna make my first claim now, which is that F is not differentiable at 0. Okay, so what we can do is we can remember the definition of differentiable. It would be, so let's consider the limit as x approaches 0 of f of x minus f of 0 all over x minus 0. This would be the definition of the derivative at 0, if it exists, right? So we're not sure yet if it exists, but let's just plug some stuff in here and see what we think. So the denominator is x. The numerator is absolute of sine of x minus absolute sine of 0, but sine of 0 is just 0. So that's it. This is your limit right here. So the question is, does this limit exist? And our claim is no. What's a good way to disprove that limits exist in this class?
Sequences.
Using sequences, exactly. Maybe we can create sequences that converge to 0 that produce images under this quotient that would suggest different limit values. What's a good sequence that converges to 0?
1 over n.
1 over n, that's my favorite one. So consider xn equals 1 over n, clearly converges to 0. But then the limit as n goes to infinity of absolute of sine of 1 over n divided by 1 over n, that's what you'd be looking at. This would be equal to the limit as n goes to infinity. We don't need those absolute value parts, guys, because sine of 1 over n is positive. Divided by 1 over n. Does anybody know what that limit is? Sine of theta over theta. It's 1. Yeah, it is. It is actually 1. A couple ways you could see that. One of them involves a Taylor series, which we didn't really talk about so much here. But if you wrote down a Maclaurin series, I guess it's called, for the sine of x, you'd see that it was x minus x cubed over 3 factorial and so on, all those later terms go to 0. You just get x over x, which is 1. This is just equal to 1. This is kind of a well-known limit. So the limit as theta goes to 0 of sine of theta over theta is equal to 1. You guys are welcome to just use that one. If that ever comes up, feel free to just use it. So that limit is just 1. So if the limit as x approaches 0 of absolute sine of x over x exists, if it exists, then it better be equal to 1. Because we found one sequence converging to 0 such that the limit of this quotient is 1. And that would mean that if there was any other sequence that converges to 0, we should also get 1 for the limit of the same thing. Is there another sequence that we should maybe think about here?
-1 over n.
How about -1 over n? I'm gonna go right here below and write another sequence down. I love it. Y sub n equals -1 over n is also converging to 0. Absolutely true. And so then, in this case, the limit as n goes to infinity of absolute of sine of -1 over n divided by -1 over n. Try to work this one out. The sine of the negative of an angle is the same as the negative of the sine of the angle, but since you're ultimately going to take the absolute values of that, the minus sign that might be floating in or out of here eventually evaporates in the numerator. It does not evaporate in the denominator, however. So what will happen is this will become the limit as n goes to infinity of, it'll just be sine of 1 over n again. Is everybody following me on that? This minus sign comes out and then gets canceled by the absolute value. So it's just sine of 1 over n on top, but then you have -1 over n on the bottom, and now that minus sign just pulls out of that limit and you get a -1. You get a -1, and so since we got two different limits for f of xn versus f of yn, then there is no single L value for this limit. I forget which proposition that is. That's actually back in earlier in chapter 4. It might be proposition 4.1 or theorem 4.1. Anyway, so therefore, the limit as x approaches 0 of absolute sine of x all over x does not exist. That's going to be the conclusion there. And so f is not differentiable at 0, and so we put a no on that. That would be a no for sure. So far, so good? Now, even though it's a no, and technically that means we can't use corollary 5.4 to address uniform continuity, the idea of sort of some kind of a maximum steepness, you can still kind of make sense of that in terms of the intuition. If there's a bound on the steepness of this picture, even if there's a corner where the graph doesn't really have a slope, but if you could say that, well, but as I come in towards that point, right, the rise over run is somehow bounded, then you could still, at least for the purposes of intuition, kind of act the same way as what corollary 5.4 would tell you. Based on that, what's your gut feeling tell you about? I'm pretty sure this one is a yes, because I can draw this picture without picking up my pencil. But the real question now is, what about uniform continuity? Because if it is uniformly continuous, I would just as soon prove that, because it will imply the other one. I don't want to do 2 proofs if I only need 1. Because remember, uniform continuity always implies continuity on any interval whatsoever. It's only the reverse that requires a closed interval. So if this is a yes, we don't have a closed interval, so I can't say this is a yes for sure. So what's the intuition that you have for that? Do you think it's going to be true?
Yeah, cause the slope's gonna be between 1 and -1.
Yeah, it's so funny, the square root of x function that we looked at just a few minutes ago kind of has a little bit of the same shape, at least out of the gate, as you're coming out from the right of zero. But this guy has basically an infinite tangent right there at zero, because the derivative is 1/2 square root of x. This one does not have a bounded derivative because it's infinitely steep as you head towards zero there. But this one, sine of x, basically is a 45-degree angle as it comes into zero. A sine of x over x has a limit of 1, which just means that kind of the slope of the sine function and the slope of just x itself are about the same as x approaches zero, you see. So my intuition is exactly what John's saying, is that there is sort of a bounded derivative here. Even though technically it was not differentiable at zero, my intuition is that essentially the idea behind corollary 5.4 is still gonna work. I'm not gonna quote theorem corollary 5.4, I'm not gonna use it because it doesn't apply if the function is not differentiable. But I can still kind of use it as a motivation to make the claim, which is what I'm gonna do right here. I'm gonna make the claim that this f is uniformly continuous on R. Okay. And so let's try to prove that. And again, I'm gonna do it from the definition. So for the proof of this claim, let epsilon greater than 0 be given. Good way to start. And again, if I want, I'm not sure if I'm gonna need this yet, but since we did it on the earlier problem, I'll just go ahead and start off this way here too, which is, we can assume that the x is greater than or equal to y. And I'm gonna come over to my scratch work now. So we're gonna have an x and a y that are kind of on an equal footing, and we're looking for a delta. And we're looking at this expression, absolute f of x minus f of y less than epsilon. That's ultimately what we want to have. And let's feed in what our function is here. So I'll do a double arrow in this, guys. Be sure with your scratch work that you've got your arrows going for me, so that I can connect things up logically. So this will be the absolute value of absolute sine x minus absolute sine y less than epsilon. Does that look like anything we've ever had?
Triangle inequality.
Thank you. Amber remembers, right? So if you had absolute of absolute x minus y, that was always less than or equal to just absolute of x minus y. There was a result. This goes back to chapter 2. And you can just use that. So if this one is less than epsilon, then this one would be. So I'm gonna do a backwards arrow only right here and put absolute of sine x minus sine y and less than epsilon there. Okay, so I can get away with that, because if this is true, then this one is true, because the left side only got smaller as I went up. Right? Well, guys, but this is just this is just what you would have for sine of x function, which is continuous. So what I'm saying is that forget the absolute value around this thing. If we just had sine of x, right? Actually, if we just had sine of x, we would have something differentiable. The derivative would be cosine of x, which would be bounded on any interval we want whatsoever. And so therefore, this function would have been uniformly continuous, meaning that given an epsilon, we can always find a delta. So what you can do here is you can say, since sine of x has a bounded derivative on R, then sine of x is uniformly continuous on R. So I've dropped the absolute value for the time being to make that observation. The sine of x is uniformly continuous on R. Now, how does that help us? Well, the definition is that given an epsilon, there does exist a delta for the sine of x. Okay, so thus, just using the definition of uniform continuity, right? There does exist a delta greater than 0, such that if well, we can just go ahead and assume x is greater than or equal to y again. Then absolute of sine of x minus sine of y is less than epsilon. And now we just go to our scratcher and run it backwards. So that's the statement we have here. Run that back to here, and now the original f of x, which is the one that does have the absolute value bars on it, is going to be uniformly continuous. Okay, so let's finish that out. So retracing the scratch. So your delta here, guys, is actually just the same as the epsilon. Retracing the scratch, we conclude that f is uniformly continuous on R. Thus, f is also continuous on R. Uniform continuity is stronger than continuity, so you can for sure put a yes on continuity. So I've got yes, yes, and no so far. So one of these problems takes a little while because there's quite a bit to it here. But I'm glad we're doing it because it kind of reviews a bunch of stuff kind of all at once. Questions here so far? Well, we haven't talked much about Riemann integrability so far today. We're certainly we're gonna do a group work tomorrow, which will be a review group work on Riemann integrability as well. So we'll get a little extra dose of review there. But what do you think on the interval 0, 1? Do you think this would be Riemann integrable? And do you have a reason? By the way, 1 is approximately right about there. This is pi over 2, which is about 1.6 or something. So you're talking about this part of the function only. I didn't want to say Riemann integrable on R because that would be talking about trying to add up the whole, that would be an improper integral. We haven't talked about Riemann integration other than a closed interval. So it wouldn't make sense for me to ask you about Riemann integrability except on a finite closed interval. But what's your gut feeling on this? Do you think you would be able to do this integral or not? And you're allowed to, for your intuition and gut feeling part of the question, you're allowed to remember your freshman calculus class and say, yeah, I think we could integrate that back in 150A or something like that. So you could say that. So based on anything that I've said so far, do we have a feeling here whether it's gonna be yay or nay? Feel pretty good about it, young? Yeah, and that's exactly right. This is a yes. This is gonna be a yes. Okay? And what I need now on that is, so I claim that f is Riemann integrable. I'll use my script R notation that we've been using in class, that it is Riemann integrable on that closed interval. I mean, heck, you guys could find an antiderivative and evaluate it and do all that stuff. That we have not learned. So guys, on this exam, no fundamental theorem or calculus, except if you wanted to check your answer. Let's say I asked you to prove that the integral of, this is the one I did the other day, of x squared from a to b is b cubed minus a cubed all over 3. If you want to check your answer by remembering how antiderivatives work and evaluating them at the endpoints of the interval, that's fine, because check your answer however you want. But that would not be your proof. That would not be your solution. So anyway, here really doesn't pay a lot of dividends to try to actually figure out what the value of the integral is. I just want to know, why is it Riemann integrable? Does somebody think they might have a reason? Really don't want to do all of that setup of partitions and big MIs, little MIs, and all that kind of stuff.
Are we gonna have to do that though on the exam? Because I was just thinking that same thing.
It would be surprising to me that there would be nothing on the exam where you had to do a partition or do an upper. That one I
I'm
did
not
in
saying at all. I'm
class-
saying on a question like this one where you're just
Oh.
asking, like if it is integrable or not. My
Um,
intuition says yes, and then my first thought was I need to find a least upper bound and a.
Actually, Amber, so what'd you say?
Increasing is always.
Okay, we had a theorem. We have a theorem 6.9, which says that if the function is monotone, now this function is not monotone on R, but it is monotone between 0 and 1, right? Since f is monotone on 0, 1, f is Riemann integrable on 0, 1. Now, I told you at the start of this review session that if there was a result that was from the next section, I think this is actually from section 6.4, it's actually on page 128 of the book. This technically is outside of the scope of what is going to be on the exam, but if you remember this result and want to use it, you can. All right. So this one might be worth knowing, just to save yourself the headache of it. However, what was the point I was trying to make with Amber?
I was talking about least upper bounds and.
Yeah, that would not be my first thought. If I'm only being asked to prove if f is Riemann integrable or not, my first thought would be theorem 6.2, which is that a function is Riemann integrable if and only if for all epsilon greater than 0, there exists a partition of my interval such that UPF minus LPF is less than epsilon. That actually would be my first thought. And what you could do here is you could, so if you didn't remember the theorem 6.9, what you could do is you could make a partition, and you guys all know how to do that P sub n partition, right? That's the most natural one to use. Normally, that's a good one to use. So what you could do is you could say for a natural number n, which I don't know what n I want yet, but what I could do is I could define P sub n, which is in the partitions of my interval 0 to 1. I could just make that as my partition. And then here, the delta xi's are all 1 over n. In general, it's b minus a over n. But in this case, a and b are just 0 and 1. And then I could just say, okay, so then UPF minus LPF. And why am I looking at that? It's because of theorem 6.2. It's one of the bullet point items on the list. You definitely want to know it. It says that f is Riemann integrable if and only if this guy is less than epsilon. This should be P sub n and P sub n here. So U of P sub nf minus L of P sub nf, I want that to be less than epsilon. If I actually calculate it though, it's a summation, I going from 1 to n, of big Mi minus little mi times delta xi. So this is the formula. And all of my delta xi's are just 1 over n, so I can pull those out. And so then all I'm left to do, guys, is to do, big M1 minus little m1, plus big M2 minus little m2, big M3 minus little m3. And if you remember the proof of theorem 6.9, what happens is because this thing is increasing, right? If I take one of my subintervals, the big M, like the big M1 right here from this first subinterval is equivalent to the little M2. And so you might remember that what happens is each one of these big M's cancels one of the little m's because they're equal. The only terms that don't cancel are the last one, which is the big Mn, and the first one with the little m1. So the rightmost maximum doesn't get canceled by anything, and the leftmost minimum value doesn't get canceled by anything. And what are these numbers? Well, big Mn is just going to be the sine of 1. And little m1 is just going to be the sine of 0. Are you with me? Because the little m1 is right here. The first subinterval, what's the minimum value? It's right here. And what about the last subinterval, which is way over here? That's the big Mn right there at sine of 1. It's because it's increasing. So in other words, what I'm saying is if you didn't remember this theorem, you could essentially reproduce how it works by just doing UPF minus LPF. And then this thing is going to be less than epsilon as long as what? Somewhere up here, I'm going to choose n to be greater than, I just have to do the math in my head here, sine of 1 over epsilon. So if n is actually, by the Archimedean principle, if you choose n to be greater than the sine of 1 over epsilon, then this will be true. And so f is Riemann integrable on the interval 0 to 1 by theorem 6.2. Again, you could just write theorem from class and I would take that. I don't have to have the numbers. So if you remember this monotone statement, you can use it. If you don't remember it, you don't need to panic. You have what I consider to be the first thing that would pop into my head here would be to use theorem 6.2, which, by the way, you noticed I got kind of excited about that theorem because I like it a lot. It's a really handy result to use. So I would be very surprised if that doesn't show up somehow at some point. Yeah. Okay. Everybody okay out there? Lindsay?
So for a ticket delta I, it's normally.
B minus A divided by N. In this case, the A and the B are just 0 and 1. Yeah.
So it'll be somewhere in between. And then for the n greater than sine 1 over e, did that just come up?
So sine of 0 was 0. I didn't really mention that. So then looking at this is what I ultimately want. I want the sine of 1 over n to be less than epsilon. So if I have my n like that, then I can move the equation around and get sine of 1 over n to be less than epsilon. So technically the epsilon is fixed. Did I ever do that here?
You did not use your rubber stamp.
I did not use my rubber stamp. Oh my gosh. Let epsilon greater than 0 be given.
Minus 10 points, Dr. Innan.
I'm taking off points right now. There's plenty of red pens up here for me to use too. Yeah, for sure. That should have been the first thing I wrote down. Okay. Yeah, theorem 6.2. Let epsilon greater than 0 be given, and then come up with the partition. I was so sidetracked into the partition. This is really the scratch work, right? Technically, and then you ultimately solve for n, and then technically the proof begins here. choose this to be the n, and I kind of just went back and inserted it into the right spot within the proof. Yeah. Okay. Okay, shall we try another one, guys? How am I doing on my time? Oh, so far, so good. I've done four problems. Okay, now I'm not going as fast as I was before. That's because this one took a long time. There was a lot to it. And I think that's fine to really discuss a lot of aspects of one problem. But let's move on to something that I think will go quite a bit faster. Okay, so number 5. As long as we're talking about Riemann integrals, why don't we do this one? I'm gonna let C be just any real number. And I'm going to suppose that F is Riemann integrable from A to B. So we have a function that's already Riemann integrable, and then I'm going to define a new function, G. You're gonna see one of these in the sample test too. I like doing this, which is I like to take something that's Riemann integrable and I like to tweak it and ask you to prove that it'll still be Riemann integrable. In this case, what I'm gonna do is I'm actually gonna shift the entire function over so that G has a new domain. G is gonna go from A plus C comma B plus C to R via G of X equals, so how am I gonna define this? I'm going to define it to be F of the quantity X minus C. So you can imagine what happens here. You plug in an X value that's in this interval, and then how do you evaluate it? Well, you subtract C from whatever X is. Well, if you subtract C from something that's in this interval, you'll get something that's back in the interval AB, and you take F of that. So that's basically what's happening. And then what we're gonna do here is show that G is Riemann integrable on the domain from A plus C to B plus C. And I wanna actually prove that the integral of G from A plus C to B plus C, if we set up that Riemann integral, I actually wanna look at the value of it now and prove that it equals the same value as the original integral of F from A to B. This is a nice little problem. Okay. So let's see. So there's kind of two parts to this. First part is just proving that G is Riemann integrable. And then we got to prove that the value of that integral is the same as the value of the original integral. So I think it intuitively makes sense. If you have, if you have a domain from A to B and here's your function F, right, whatever. So then this function here is really the same thing as if you come over here and you shift everything over by C. And now G is gonna have exactly the same shape as F, it's just got a shifted domain is all. So I mean, I'm not surprised that the amount of area here, for example, which is what we sometimes think of the integral as representing, it should be the same area as that. Seems pretty reasonable. Okay, but let's take this one part at a time here. Let's try to prove that G is Riemann integrable, first of all. And what approach would I probably use for that? I ask you to prove that a function is Riemann integrable. Pardon me? The theorem 6.2, that given the epsilon, that there exists a partition such that UPF minus LPF is less than epsilon. Yeah, absolutely. That's exactly what I would do. So for this first part, I'm gonna start off with my good old let epsilon greater than 0 be given. Now, the key thing here is gonna be that we need a partition, and it needs to be a partition of this interval. And is there a way that we would obtain that partition?
No, there would already be a partition because of F.
Because F is already Riemann integrable, there's already, for the epsilon that's given, there already exists a partition of this interval. Now, that's not the same interval as this one, but let's at least try to use that to help us. So by theorem 6.2, applied to F. So F is already Riemann integrable, so if we apply theorem 6.2 to F, there already exists a partition. Now here I'm gonna be really explicit as to what the interval is, so it's the interval from A to B. So there exists a partition from A to B, such that U of PF minus L of PF is less than epsilon. And by the way, sometimes when there's a C, so far the C hasn't shown up anywhere here. Sometimes when there's a C here, you find out later that, oh, maybe this needs to be epsilon over C or something like that. We have to be, keep open-minded about it, that maybe we have to shift this epsilon somehow to make the proof go. I don't know yet, but we can start off with the same epsilon that we started from and just see how that works. I'm gonna actually write down the partition in some explicit notation here. I think this would be helpful. We start with A, and then we have x1, and then we have x2, and so on. And then we have xn minus 1, and then we have B. So that's the way the partition of the interval AB would look. So given that partition, the question is, though, we would like to know whether G is Riemann integrable, so we need to know if we can make a partition of this interval. We have that partition. Would there be a way of creating a partition on this is a different interval. Can we make a partition of this interval somehow by taking advantage of the partition that we already have in front of us? We could literally take all of these points, right, which are just, they're just points along here, right? And we could literally just add C to all of them, and we get the exact same kind of just spacing or distribution of the points over here, right? So then let's form a new partition. I think in my solution to this, I called it P sub C. And this was just the partition that goes A plus C, and then x1 plus C, x2 plus C, and dot, 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 and finally B plus C, right? So you just add C to everything, and this is certainly in the partitions of A plus C, comma, B plus C. So that is a partition that we can look at. So now, what we have to do is see whether that partition has the upper minus lower less than epsilon, okay? For G, for the function G, right? So what we want to do is we want to calculate U of P sub C of G minus L of P sub C of G. Okay, so this would be, a summation as I goes from 1 to n of, I'm going to write this as m sub I, I'm going to put a super G on that, just to emphasize we're talking about the function G, minus little m sub I of G times delta of xi. Now, are those delta xi's any different than the delta xi's that we would have had for the original partition P? They're not. The way I've sort of chopped up the interval, right? The spacing between successive points that I've used has not changed. So these delta xi's are the same as they were when I was doing UPF minus LPF. And then what about big MI? So let's take one of my subintervals here. If I take, I don't know, maybe this one right here, take this little subinterval and I think about the big MI for this subinterval, it's gonna be like right there, for example, right? Is that any different than the corresponding, I guess it would be this one, the big MI that we would have had right here? No, not at all. That maximum value matches that maximum value. So in other words, and that doesn't really need an explanation, it's just kind of clear. This can just be replaced as a summation of capital MI of F, so now I use a superscript of an F here, minus the little mi of the F, and as I already explained, those delta xi's are the same. And so this becomes just UPF minus LPF. And sure enough, that is less than epsilon. That is going to be less than epsilon, absolutely true. And so we're good to go on that. We're good to go on that. How do you guys feel about this problem? I really like this problem. I could tweak this a million ways. I could, instead of g of x equals f of x minus c, I could leave the interval the same, but I could say, well, g of x is going to be f of x plus c, or minus c, or times c. I think the one in the sample midterm is g of x equals f of x times c, and I even made it, must have been in a bad mood. I said c is less than 0. If c is less than 0, what happens is the big m's for the f function turn into the little m's for the g function, because the maximum values, if you multiply them by a minus sign, maximums turn into minimums and minimums turn into maximums. So you get something that's like this, but then the big m's and little m's are getting like tangled together and stuff like that. So there's a sample midterm question for you to try to kind of practice that. But yeah, so this is a common theme, that if we start off with a Riemann integrable function, how can we make other Riemann integrable functions? I think there's even one of those even for the homework for tonight. And an example like that too, where there was an interval from A to B, and then there was an interval from B to C. And then I said, well, what about Riemann integrability from A to C? So changing the interval is one way I can do it. The other way I can do it is I can change the way the function is defined by shifting the f in some other way. This is one way to do it, but there'd be other things that you could do as well. So if you are feeling ambitious, so you get to Wednesday, you're like, I did the sample test, I've studied everything, I need to do something. You could take something like this and just see if you could tweak it for yourself and try it out. And if you get stuck, you can always ask me. Okay. What do you guys think? Feeling okay? I want to do one more tonight. Sorry? Oh, I didn't finish. I just proved Riemann integrability to G. You're absolutely right. I need to do the other part. Can I erase this part of the solution? Yeah. Okay, I need to do the second part of this, and then I'm going to do one more problem as well. You know, I know it's going to take me a little past 9. I want to talk about one other topic that we haven't talked about tonight that I think we should. But before I do that, let's check this out. Okay. Guys, one way to prove that two numbers are equal to each other is to subtract them and show that it is less than anything you want it to be. So what I'm going to do for the second part, I'm going to let epsilon greater than 0 be, I normally say given, and that's fine, but I'm going to say arbitrary here just to kind of make my point a little bit better. Because what I'm going to do is I'm going to claim, hopefully, if I do it right, I'm going to claim that the absolute value of the difference of these two things is, so So if I take the absolute value of the integral from a plus c to b plus c of g minus the integral from a to b of f, I claim that that's less than epsilon. Since I have absolute value bars on that, of course it's at least 0. Can't be negative. But could it be possible, if these two numbers were not the same, if they weren't, of course we know that they are, but if they weren't the same, then I could probably squeeze a small enough epsilon for which the difference would not be less than that epsilon. So if I can prove this claim, I'm proving that, how far apart are these two things? Well, they're not very far apart. You give me any arbitrary positive number, oh, your integrals are not even that far apart. And you can kind of imagine, it's almost like if you took a limit as epsilon approaches 0, you would squeeze the difference of those two integrals down to have to be 0. It cannot be anything positive. Okay, so now how am I going to do this? Well, what I do know is that for any partition P of the interval from A to B, I do know that the value of the integral of f, that one, just this, not going to talk about g yet, just want to look at f. Okay, so this is one thing we learned, guys, is that the exact value of that integral is always less than or equal to any upper sum that you could ever calculate. And it's always greater than or equal to any lower sum. So if you make any partition, doesn't matter what it is. Right, I mean, basically the lower Riemann integral, right, is the supremum of all the LPFs. It's an upper bound for all the LPFs. So this LPF is less than or equal to the supremum of all the LPFs, which is the lower Riemann integral. Which in this case, we are assuming that this is Riemann integral, so it's the same as the upper Riemann integral. And the upper Riemann integral is always less than or equal to any particular upper sum. So what I'm writing here is nothing deep. You give me any lower sum, you give me any upper sum, the actual integral, if it exists, the actual integral must be between those two. You can do 5 billion partitions here, and every one of those LPFs will be less than or equal to the exact integral. 5 billion partitions here, and every one of those upper sums will be greater than or equal to the actual integral. So we certainly know that. And then likewise, for any P sub C, which is a partition of A plus C to B plus C, the L of P sub C of G has got to be less than or equal to the integral from A plus C to B plus C of G, which is less than or equal to U of P sub C of G. Okay, but remember guys, that this is kind of coming from the part that's been erased now. The lower sum of G relative to the P sub C partition is exactly the same, because the big M sub I superscript F is the same as the big M sub I superscript G. This is just L of P F. Yeah, and this one is just U of P F. So, how far apart are these two guys? Less than epsilon. And that's the same as these two guys. And between those two values, so let's just put it this way. So since U of PF minus L of PF is less than epsilon, I'm specifically using the same partition that I did in the first part of the proof here. then the question is, how far apart can these two integrals be? So it's like LPF is here and UPF is here, right? And the integral of F is somewhere in between. And the integral of G is somewhere in between. So they're both kind of somewhere between that end and that end of the table. And how far is the whole width of the table? Epsilon, right? Less than epsilon, right? And now you got these two numbers that are kind of between the ends of the table. So how far apart are they from each other? Well, definitely no farther than the width of the table, which is epsilon. So that's really the reason that this claim now is true. Okay, so since and the integral of f from a to b and the integral from a plus c to b plus c of g are between LPF and UPF, since they're in between those values, then they can't be very far from each other, right? So then the claim follows. The claim follows at once. Yeah. So that's how you get the final conclusion there. Claim follows immediately from that. What do you guys think? Seem reasonable? Yeah, so just really make sure you have this idea that once you have a Riemann integrable function, that means that the upper and lower Riemann integrals are equal. And it also means that any lower sum will be less than that thing, and any upper sum will be greater than that thing. So if you've got UPF and LPF within epsilon of each other, then the exact value of the integral has to be right within that interval of with epsilon. Can't be any farther apart than that. It's got to be, it's not often no man's land. It has to be between those two values. Yeah, that's kind of the point. Questions here? I know there's one in the sample test that is in the same spirit as this, and so it'll definitely be worth taking a look at. Okay, and like I said, we're going to do some more group work about Riemann integrals tomorrow. I said I wanted to do one more problem. Are you guys up for one more problem, or is it too late? I can also stop and just do this on Wednesday. Okay. You guys okay? I'll do, because there's one thing I have not talked about, and that is Taylor's theorem. And I just graded that homework, and there were a few issues with it. So I thought maybe I would just do one last example, which would be number 6, and then I will make this the last one though, so I can go to my office hours. I know some people are still working on homework, that kind of stuff, so I don't want to go too long tonight. But let's do one last problem. So this is number 6. My markers are barely going to last for one more problem anyway. So let's do this. Show that for all x greater than or equal to 0, we have 1 plus a half x minus 1/8 of x squared is less than or equal to the square root of 1 plus x. Okay. So this is proving an inequality, and does it kind of look like a problem on Taylor polynomials, Taylor theorem, that kind of thing? Whenever you have a function that's being estimated using a polynomial, you want to be thinking about Taylor's theorem. And you might even want to get so specific as to say Taylor's theorem with n equals a certain value. In this case, what value of n looks promising? Could be 2, could be 3. Sometimes, here's the reason, is because Taylor's theorem talks about estimating your function by using a polynomial of a certain degree, but then there's a remainder term that's 1 degree higher. So whether this x squared part actually represents a remainder or whether it's actually part of the polynomial is not always clear from the beginning. And so we might have to do a little work to figure that out. So I would probably suggest we start off just taking it at face value with n equals 2 and try to write down the Taylor polynomial of degree 2 for this function. So I'm getting ahead of myself. We need to write down the function. Okay, so we have, so we let f of x equal the square root of 1 plus x. And then if I'm gonna do the second Taylor polynomial, then I'm gonna need 2 derivatives of this, right? So, and then we also need a base point. And the base point is usually obvious from the form of the polynomial. You can kind of see, because normally the way the polynomial looks is, f of x naught plus f prime of x naught times x minus x naught. So you're seeing the x with something subtracted from it. In this case, I don't see that at all, and so I'm just gonna assume that that's because we're subtracting nothing. And so we'll try it with x naught equal to 0. I don't want to write out the whole Taylor theorem, if that's okay. So it basically says that, well, first of all, let's write out the polynomial, the Taylor polynomial. So before I get into the actual remainder theorem for the Taylor's theorem, let's just write out the polynomial. So I need to take a couple of derivatives of the square root of 1 plus x. So the first derivative will give me a 1/2 and then a 1 plus x to the minus 1/2, which I can write as a square root of 1 plus x in the denominator. And I'm gonna go to a second derivative as well. So I'm gonna take another derivative. Again, I can think of the 1 plus x as having a negative 1/2 exponent. When I pull that down in front, I will get a negative 1/4. And then this will be 1 over, let's see. So it'll be 1 plus x to the 3 halves, right? Yeah, so we just jack that power up by 1 there. So that looks to be correct to me. And so if I evaluate those at x naught equal to 0, then when I plug those in, I get 1/2 for this one, and I get negative 1/4 for this one. So I just get those derivatives evaluated. And so now let's go ahead and write down the second Taylor polynomial. So P2 of x, right? That's the notation for the second Taylor polynomial. And what it equals is, as I just wrote down a minute ago, it is just f of x naught plus f prime of x naught times x minus x naught. I'm gonna put it in 0 for x naught in just a second. And then plus the second term is 1 over 2 factorial times the second derivative of f at x naught times the quantity x minus x naught squared. Okay, and here I'm going to evaluate this with x naught equal to 0. So f of, let me just plug that in first. So f of 0 plus f prime of 0 times x plus 1 over 2 factorial times f double prime of 0 times x squared. There's your simplified Taylor polynomial of degree 2. And now I'm going to just plug in 0 into my function, and I get a square root of 1, which is just 1. And then f prime of 0, actually we already did that one, it was 1/2 x. And then f double prime of 0 was negative 1/4, and when you combine that with the 2 factorial, you get minus 1/8 over x squared. Guys, it is a good sign that you got for the expression, you got exactly what was part of the question here. Right? What was part of the question. Now, one thing I think has been confusing people a little bit about this is that this is not, what we've done so far is not Taylor's theorem. What we've done so far is just evaluate a Taylor polynomial. What Taylor's theorem is about is the remainder term, which is really representing the error in our approximation. So keep that in mind that we aren't really using Taylor's theorem to write this down. We're just saying, all right, by definition, this is the second Taylor polynomial. Plug in the numbers, take the derivatives, evaluate it, and write it down. That's what we did right here. Okay. Now, what we know is that, so I would actually like to show that this is less than or equal to f of x. So the relationship between the Taylor polynomial and f of x, that's getting towards Taylor's theorem. That's the remainder, right? So recall from Taylor's theorem that f of x is p, in this case 2 of x, plus r2 of x. And now I'm going to remind you what the remainder is, because this is the important part for Taylor's theorem. R2 of x is equal to, so first of all, there's a denominator of a 3 factorial. And then in the numerator, what you have is 3 derivatives of f, but it's evaluated at c. So just to remind you about that, and then it's still got an x minus x naught, which in this case is just x, that's being cubed here. Okay, and let's just write it down very carefully. This is where c is between, according to the theorem, it's between x naught and x. X naught is 0. And x, well, x was greater than or equal to 0. By the way, if you wanted to do the x equals 0 case just directly, you literally plug in 0 for x and confirm that this is true for 0, so that then you can actually have an interval, you know, from 0 to x. Sometimes you want to have a full-blown interval. If I write this interval down, it's sort of assumed that x is greater than 0. So there is a special case here, which is when x equals 0. That would amount to just plugging in 0 on both sides of the inequality and just doing a little check on it. It's kind of a technicality. I wouldn't get too worried about that. But ultimately, you do have an interval here, and your c is within that interval between 0 and x. Well, the point is, oh, I need 3 derivatives though, don't I? I need to come up with a 3rd derivative. Oh my goodness. Let's see if I can do 3 derivatives at 9 o'clock at night. That'll be interesting. So negative 1/4, and I'm going to pull down a negative 3/2, right? It's really a negative 3/2. So is that 3/8? 3/8, and then my power on the bottom of the 1 plus x goes up to 5/2, I believe. Whew, okay, and so we're evaluating that at c. So let's plug that in here. That's going to be 3/8. And then there's a 3 factorial on the bottom. And then there is a 1 plus c to the 5/2 also on the bottom. And then there's an x cubed on top. But the main thing is, okay, it looks bad, but it's actually not. Because all you really need to convince me is that it is greater than 0. Because I want to know that f of x, what am I trying to prove here? I'm trying to prove that my second Taylor polynomial, which is what we evaluated that it is in the question, that is less than or equal to f of x. I want this to be less than or equal to this. This one less than or equal to this. That would just mean that r of x should be greater than or equal to 0. Which that part, guys, is actually clear. Because x is positive. C is greater than 0 also. They're both positive. X is positive, C is positive, so your numerator is positive, your denominator is positive. The point is, this is for sure positive. And again, if x was allowed to be 0, this would be greater than or equal to 0. So if you dealt with that as a special case, then you can make this a strict greater than. And the point is that that implies that P2 of x is less than f of x, which is the same as the problem that you're being asked for. Yeah. So this would technically be for x is greater than 0, and then when x equals 0, you just directly get equality on both sides. So that's just a minor point. That seem okay? Now I have a part B here. And we won't dwell on it. I did tell you, didn't I, about years ago when I would do the review sessions and then go for 6 hours?
You
8
told,
hours.
you told the 471 class last semester.
Every semester I remind people, when I was a grad student, I was 20 something. I was running all around we would take a dinner break. And I'd be like, oh yeah, that'll send them home. Nope, they all came back an hour later and just picked right up where we left off after like 6 hours. And so I used to do that. These days I don't have that kind of energy. And at some point I remember I asked the students in one of the reviews, so if I don't show you any more problems, will you then go home? And everybody said yes. They just didn't want to leave as long as I was showing another problem. Like, that could be the question on the test. And that was back in the day when I wasn't even the one writing the test. I was just trying to help the students get ready for their professor's exam. So anyway, let me just really quickly do parts B and C. Very quick, I promise. Use part A to estimate the square root of 1.3.
Problem B sub 1.
Now, part A of that is, yeah, and 3 hours later, we're still working on it. No, so this is an easy one, because it says use part A to estimate the square root of 1.3. So you can imagine that we're just talking about an x value of 0.3. And if we're using part A, it means we're using this expression here to do that. So what we're gonna do is, for the solution, evaluate P2 of x at a value of 0.3. So I'll evaluate at 0.3, and so that's just going to be 1 plus a half times 0.3, and then minus 1/8 times 0.3 squared. And now this turned out to be a kind of a messy number, and I remember saying to myself, well, I wouldn't, without a calculator, I wouldn't worry about it. So don't worry about it. If you just left it like that, I'd take it. Like, that would be your estimate, and I'd be like, okay, that's fine. Answer. My pages have gotten all out of order. Oh, here we go. It comes out to be 1.13875. Again, I would not expect you to come up with that without a calculator. You can just leave it unsimplified, but just so you have an idea, that's what we would get. Okay, so, but what's really more interesting is part C, because all that's just plugging in, the x value into the polynomial. But part C is going to ask, and again, so far part B is not really Taylor's theorem. It's just saying, oh, I'm going to estimate the square root of 1.3 by using the Taylor polynomial. Anybody can do that without Taylor's theorem. What would be important for the application would be to say, well, how good is that estimate? Right, how good is that estimate? So I am going to ask a part C. This is the last part, which is give an upper bound. Give an upper bound for the error to your estimate in part B. So the idea here is we don't actually know what the error is. Guys, if we knew what the exact error was, we could take that error and add it to our estimate and get the exact value of the square root of 1.3. We wouldn't have to estimate it, we'd get the exact value. So whenever I ask you something about the error, it's never going to be what is the error. The question is going to be, give me an upper bound, like a worst case scenario. What's the worst that the error could be? And of course, we know that the error the error is this remainder term. Because that's the difference between, I'm gonna put absolute value bars on around it, because it could be plus or minus, but that's the difference between the actual value of the function, so absolute f of x, minus the estimated value of the function which we gave in part B, which would be P2 of x. Now, in this case, it's actually with 0.3 plugged into it. So I should be looking at 0.3 now. So let's take R2 of 0.3. So this is the absolute value of, well, it's technically, it is f of 0.3, but we don't know what f of 0.3 is, right? Minus P2 of 0.3, which is what we gave in part B. But ultimately, what you're supposed to do, guys, to evaluate R2 of 0.3 is not this, but rather this. This is how you get your estimate, right? So I'm gonna put in 0.3 here. So I have 3 times 0.3 cubed. Right? Divided by, and now down here I have an 8 and a 3 factorial, that would be a 48. 8 times 6. And now we have to ask ourselves, what is the worst that this could be? So I wanna make this remainder come out as big as possible. So I'm gonna change this, guys, to a less than or equal to. Right? To make this a worst case scenario, I wanna make this fraction as big as I can. To figure out, well, what's the worst it could be? To make the fraction as a whole as big as I can, I'm going to make the denominator as small as I can. And the denominator, as you can see, is already 1 plus c to a power. So it's more than 1. The c is between 0 and x. So even if c was 0, this would be a 1. And if c was larger than 0, that would only make the denominator bigger, which would make my remainder smaller. If I want the upper bound, the worst case of what that error is, I'm gonna put in c equals 0, which means I just have 1 to the 5 halves on the bottom. That's it. So this is gonna be it. And again, without a calculator, this is annoying. This is just 0.0016875. So again, no calculators on the exam, and in some ways that's gonna be better for you. So you're not fumbling around with calculators so much. This is a theoretical course anyway. I don't wanna sidetrack us with a bunch of calculator problems. But that's basically how something like this would work. So the Taylor's theorem part of it is this remainder formula. Okay, that's really, I know the statement of Taylor's theorem is much longer than this, but how you're using Taylor's theorem is to do exactly this kind of a part C, giving an upper bound on an error by using the remainder formula, which comes from Taylor's theorem. So Taylor's theorem is not just evaluating P2 of x. Anybody can do that without a theorem, right? The Taylor's theorem part is really this part here. Okay. So guys, tonight we've touched a little bit on uniform continuity using the definition. I haven't done everything, but talked a little bit about uniform continuity. We've certainly talked about differentiation, applications like the mean value theorem. I think the definition of the derivative came up at some point. We used the product rule somewhere, the chain rule, those kind of things. And then we did a little bit with Riemann integration too. I tried to hit a little bit of everything, but actually, the truth be told, I've kind of only done about half the problems that I had in mind. So on Wednesday, I'm going to come hit some of those other problems. Again, I'll be jumping around. But if you can make it, great. If you feel like this has already got you started, you can just take it from here. It's totally fine. Nobody's requiring you to sit through my examples, but I will have a good helping of some more practice problems as well. And especially between now and Wednesday, if you sort of figure out what your weaknesses are specifically. If there's something you're not comfortable with, that you want to come to my office hours, or you want to really hone in on it during the review session if it comes up. Because I'll try to bring almost everything up that I can again, just to kind of recycle the stuff over again. But so, now's a good time for you to be thinking about what your strengths and weaknesses are, where you're going to spend your time, everybody needs to get the definitions down, the theorems down. That's sort of a baseline for everyone. But then beyond that, what kind of problems are you feeling stronger with? What kind of problems are you feeling like you need to see a little bit more practice with? And I think by coming tonight, 3 days ahead of the exam, you've still got some time to sort that out and ask the questions if they come up. So, anybody have anything for me before we kind of adjourn for this session anyway? So far, so good. The idea is not that we're walking out of here feeling like, oh yeah, I can just take the test now or kind of thing. No, this is more of a, let's just kind of get the lay of the land. Let's figure out, well, where do we need to put in our time? So I'll let you spend some quiet time figuring that out, and then you can certainly bring me some questions. So, all right, I'm gonna go ahead and sign off from the Zoom, guys. I will be going over to my office hour Zoom if there's anything anybody wants to talk about, or in person if you're here. Because there is still some homework due by the end of the night. I'm gonna stick around till midnight tonight. So that's my plan.
Thank you.
All right, thank you, guys.
And you're recording like, right?